If you've wondered how we know it's negative charges flowing and not positive charges flowing in a wire when current is flowing, it's due to a simple experiment performed by Edward Hall in 1879, and this experiment is referred to as the Hall effect. This experiment will also give us the density and drift velocity of the conduction particles. The Hall effect is a routine process monitoring technique in the semiconductor industry. Hall took a piece of gold that he formed into a rectangular shape like this, so he knew the thickness and the width of his piece of gold. With the coordinate axis as shown, he had a current flowing through the gold in the y direction, and he applied a magnetic field, a uniform magnetic field, in the z direction. Hall observed that with the current flowing, he would measure a voltage across the width of the sample in the x direction. We'll see that the sign of this voltage will tell us if the current is due to positive charges flowing in the y direction or negative charges flowing in the minus y direction. From the positive z direction, let's take a view looking down onto the piece of gold. Let's first look at the situation where the conduction charges are negative. So a current flowing in the plus y direction will result from these negative conduction charges moving in the minus y direction. So we can represent their velocity as mu sub 0 in the minus y direction. We'll call the magnitude of the charge E, so if the conduction charges are negative, their charge will be minus E. So the force QU cross B becomes E U sub 0 B sub 0 in the x direction. So this force will push the electrons to the right, making the left side of the gold positively charged and the right side of the gold negatively charged. If the current were due to the motion of positive charges, a current flowing in the y direction would be due to positive charges flowing in the y direction, so the velocity of those charges will be u sub 0 in the y direction. So again, with the magnitude of the charge being E, the QU cross B force would be E U sub 0 B sub 0 in the x direction. So this force would push the mobile positive charges to the right, making the left-hand side of the gold negatively charged and the right-hand side of the gold positively charged. So if Hall would have observed a positive voltmeter reading, he knew the mobile species were negative charges, and if his voltmeter had given a negative reading, he would have known that the mobile charges were positive charges. Hall observed a positive reading on his voltmeter, so he was able to conclude that the mobile species in metals were negative charges. If the only force these electrons were experiencing was the force due to the magnetic field, they would all pile up on the right-hand side of the gold. As the QU cross B force pushes the negative charges to the right, there builds up a Coulombic attraction between the non-mobile positive part of the atom and the negative charges. In steady state, in the x direction, there will be a balance between the force on the negative charges due to the magnetic field and the force on the charges due to the electric field. The Lorentz force equation accounts for those two forces, so in steady state it will equal 0. Substituting in terms for Q, E, U, and B, we can solve for the electric field intensity. Dividing both sides of the equation by minus E and AY cross AZ is AX, we can now solve for the electric field intensity. So with the width of our sample being W, the voltmeter reading will be the voltage at x equals 0 minus the voltage at x equals W, which is equal to minus the integral from W to 0 of E dot dl. So substitute our value for the electric field intensity and dx in the x direction for dl. And we see the voltmeter reading is given by the velocity of the conduction electrons times the magnitude of our magnetic flux density field times the width of our gold conductor. We know the width of our gold conductor. We're applying the magnetic field, so we know the value of our magnetic flux density field, and we're measuring the Hall voltage. So the only unknown in this equation is the velocity of the mobile electrons, so we can determine that velocity. So from our measured Hall voltage, we divide our applied magnetic field and the width of our gold sample, and we get the drift velocity of our conduction electrons. And knowing this drift velocity will now allow us to determine what is the density of the conduction electrons in our gold sample. We know the current flowing. We can measure that in our piece of gold. So the current density is that current divided by our cross-sectional area, and it's moving in the plus y direction. We also know current density is charge density times the velocity with which that charge is moving. Our charge density is N, the number of conduction electrons per cubic meter, times minus E, the charge on an electron. And we know they're moving in the minus y direction with the velocity u sub 0. We just saw that this velocity can be determined by the measured Hall voltage divided by the magnetic field intensity and the width of our sample. So then we can solve for our density of conduction electrons. So this Hall effect is also a technique that is used often, especially in the semiconductor industry, to monitor density of conduction species. The Hall effect can also be used to measure the magnetic flux density field. So if we go back to this equation here, let's solve for our magnetic field intensity. Because we'll know the material from which we built the Hall sensor, for given current flowing through the Hall sensor, we will know the velocity with which the conduction charges are moving. Then from a measurement of the Hall voltage, we can determine the magnetic flux density field. So a Hall sensor is a device for measuring the magnetic flux density field, but it's also a device for sensing magnetic fields. So for instance, covers on devices like Kindles and iPads know when you're closing and opening them because there's a magnet in the cover and a Hall sensor on the other side.